Hi. Okay. So this screencast is about the brain, learning, memory, and the development of the self. It's big learning, big information, so let's get started. We're going to jump right in. Okay. I'm going to put myself in the corner. Here I go. All right, development in the first 2 years. What's it all about? So, you might take a moment to think about that. What is the whole purpose of development in general? What are we trying to develop in children? And two, what is the specific development that happens within the first 2 years? What's it about? What's the purpose of it? The greatest thing that's going to happen? Well, it may not be a very sexy answer, but a big part of it is the laying down the basic architecture of the brain. So if we go back to the idea about neuroplasticity, that the brain is constantly shaping through neural firing and wiring, which we're going to talk a lot about here in a minute, then these first 2 years of life are an absolute momentous time for that. This is when it happens big time. And that whatever this initial architecture is the foundation. It's like if you're building a house, this is it. This is what the rest of it is going to be built upon in a lot of ways. So it's this basic architecture of the brain that will provide a strong foundation for what we hope will be optimal self-regulation, harmonious relationships, and a healthy sense of self through the lifespan. Now, please don't misunderstand me to say that if just the right architecture isn't laid down in these first 2 years, that the rest of it is just, you might as well throw it all away. No. But this is the time when neuroplasticity is strongest, when the plasticity of the brain is easiest. And so, and yes, whatever happens here will be built upon. And then when we get to adolescence and adulthood, this will be the brain we have. And if we become kind of awakened to what that looks like and what that means for us, we can begin to make changes to change some of that. But this is the origins of our architecture. It's also about, I think, these first 2 years learning to be human, becoming a functioning self in relationship with others. What it's all about to live in this world and society and your family and whatever that is, and who you are inside of that. And it's also the time when we create first schemas and working models, which are things that we'll talk about a little bit. But we talk a lot about those as we continue on, especially when we talk about attachment. Okay, so we're going to go backwards a little bit and talk a little bit about this fundamental unit of the brain, a little bit about the brain structure, just a little bit, especially the neuron. There's over 100 billion of them, collectively over 2 million miles long. Each neuron has about 10,000 connections. It can link to about 10,000 other neurons. And so if you think about that's 1 million billion potential connections, and it's a lot. So again, that's kind of a moment of awe. Oh my goodness, how amazing is this in our brain, and how complex is that? So a neuron sends an electrical impulse, an action potential along its axon, which is its sort of long piece of the neuron that comes off of the soma, the body of the neuron, and then it releases a neurotransmitter at the synapse, which is the space between two neurons, and that's going to either excite, continue an action forward, a movement forward, or inhibit that neuron to move forward. So synaptic connections are the foundation for the intricate architecture of the brain. How neurons connect together is key to everything else, to our learning, to our memory systems, to everything that we know about life and who we are. It's how these neurons connect together, so our synaptic connections. Neurons connecting together create spider web-like interconnections, and the activation of one neuron can influence an average of 10,000 others. So yes, it connects, but we have to remember, so it can impact that, the activation of so many more. And when these connect together, they create this spider web-like interconnections all through the brain. The set of neurons that fire together at a given moment can create a neural net profile. which is a pattern of activation clustered together as a whole for a common function. So when this says think Eiffel Tower, if I say Eiffel Tower to you, or, it really could be any landmark that you can think of, what comes into your mind right then? You're going to get an activation of some type of neural net profile if you've ever heard those words before. And it's going to create for you an image of that as your brain activates all the neurons responsible for that, which we're going to continue to use that example as we go. There are a number of possible firing patterns in any given moment. So that's the on and off of neurons, of those patterns, that exciting or inhibiting of neurons, 10 to the millionth power. Big stuff, big stuff. Okay, so the neuron is our basic unit of our architecture and everything of who we are, and how it communicates with all the other neurons in our brain is key to all of this, to building our memory, to everything we know and to who we are, which neurons it connects to, how they connect, the information that they carry to each other, which we'll talk about. So let's talk about these three areas of the brain. It's like a 3-scooped ice cream cone, which I kind of just like the metaphor for. So our lower areas, if we look at our little brain in the hand model, the lower areas way down here, our bottom scoop includes our brain stem, regulating arousal states, alertness, body temperature, all the things that we don't really have any control over in a moment, that are automatic. The cerebellum, which has a lot to do with our muscular activity, but it also integrates body, emotion, a lot of things in decision making as well, but it's really well known for its motor equilibrium, balance, things like that. The thalamus is a gateway for sensory information. So when you are bombarded with any sensory input, it goes to the thalamus, who then moves it out to all the other perceptual centers and sensory centers. Hypothalamus. Oh, and that thalamus is also very connected to the cortex, which is the highest part in the thinking brain. So the hypothalamus links our nervous system to our endocrine or our hormonal system, aiding in bodily equilibrium through hormonal release. So as a lot of information gets read and integrated in our system between our emotions and our thinking and our body states, hormonal release is dictated through this. HPA, which we will talk about again in adolescence later on, the hypothalamus pituitary adrenal axis, HPA axis, extremely important axis within the body. It's involved in controlling reactions to stress, as well as other bodily regulating processes like digestion, immune system, mood, emotion, sexual desire, and energy expenditure, which, if you think about it, are all somewhat related to the level of our stress. So, things go from the hypothalamus, information flows from the hypothalamus to the pituitary to the adrenals, which in turn are making decisions, as it were, about what hormones to release based on the state of everything within our emotions and our body state and everything. Okay. That's our bottom layer. Central brain structures. This is our second scoop. It's our limbic system, our emotional brain. It can get rather complicated, but this is what we're going to focus on. It helps help coordinate the activity of various regions of the brain. The amygdala, we're going to really focus on. Almond-shaped cluster of neurons, and it's involved in evaluating meaning. We don't think about that very often, but it evaluates incoming sensory information, so that can be nonverbal information that we receive from people too. Their facial expressions, their tone of voice, the gestures that they use, to determine, is this good or bad? So it uses other social processing centers too, but it's a big meaning evaluator. It assesses information that we're getting to determine the meaning of it. And it can be like a car alarm to some extent, where if, to determine if something is a threat or not, but giving meaning to situations. And it processes social cues as well, and that can be those nonverbal inputs. Big emotion, and tends to help in the activation of emotion, especially fear and anger, we hear a lot about with the amygdala. Um, it plays a crucial role in fight and flight. It obtains information from our visual system. It appraises it. The thing is that information can come into the thalamus and go directly to the amygdala. It doesn't have to go via the thinking center. So this is a back alley. And the thing is that the amygdala is much quicker to react than our thinking centers. So the amygdala assesses something for meaning, and a lot of times it's like a filing system almost, and things that have happened in the past. It doesn't hold perfect memory or anything like that, but things that have happened in the past and how we've reacted to them, it holds our emotional memory. And so it will determine very quickly what it's going to do in a situation. And we needed to do that in some situations, right? That's why it was created through evolution, to respond quickly when we didn't want to sit around and think, what should I do about that big animal coming toward me? We just wanted to be able to react. So if it appraises danger, it can send out a arousal message to start the fight or flight response, like a car alarm. It can non-consciously create now remember, it's not using our higher level thinking to consciously do these things, to create a self-fulfilling prophecy for activation in future situations. So what I mean, it's like that filing system, later circumstances can, if something causes us danger in one scenario, it can be as something like the first time we drive and we almost get hit and we're like, or we are in an accident or something like that happens. And then the amygdala can kind of file in its systems the idea of, in its neuronal systems, the idea that, driving equals danger in kind of big ways, or anytime we come in, near a car. We don't even have to remember exactly what happened years later to have that reaction to it, that kind of physiological reaction to it. Okay, so then we can set ourselves up for a self-fulfilling prophecy in the future. So the hippocampus is a seahorse-shaped cluster of neurons, and it's involved in memory, the recalling of facts, and autobiographical details, which we're going to get much more into later. It gives the brain a sense of self in space and time. It's a very contextual memory piece. For example, I think it was in London taxi drivers have a much larger hippocampus than other people because if you think about it, they're all about space and time. They're all about spatial understanding and spatial awareness. They have to know where things are and how to get there. So using that kind of information over and over again grows that part of the brain. So it links memory to emotional evaluating centers. It's right near the amygdala. So they work together and this is how this can happen for the amygdala, to link time and place with emotional memory. So memory and emotion become very intertwined, and not just memory of facts, but memory of where we are and when we were in a certain situation. All right, our upper brain structures, the prefrontal cortex, that's right up here, frontmost part of the cortex. And it's the whole cortex is our upper brain structures, but we're focusing mostly for our needs on the prefrontal cortex. The dorsolateral PFC, dorsal meaning the upper side, lateral to the sides, so kind of up to the sides, plays major role in working memory, which we'll talk about a little bit later, which is placing something on the chalkboard of the mind. The medial or middle prefrontal cortex, kind of back in here behind the forehead. This is very much the social brain. There's lots of different parts of it, so I'm just picking certain ones to kind of share. The social brain, and it's also very much linked between the limbic system and the thinking brain. So it integrates all of this information. It takes input of the thinking brain, of the emotions, of the body as well, the body state, how the body's feeling, and our relational interactions, information from other people. And it takes this information and integrates it to come up with decisions and choices and future choices and responses. So the orbitofrontal cortex, which is behind and above the eyes, sometimes referred to as the paralimbic with the anterior cingulate cortex, which was the next one, because it helps integrate the limbic and the PFC, as I kind of just said. It helps shape attachment and self-awareness, and it is shaped itself through relational experience. So the interactions we have with others tend to shape this. And the anterior cingulate cortex is a curved structure at the top of the limbic system, the bottom of the PFC, helps coordinate several functions, focus, attention, registering of body states, such as pain, and social states such as rejection. So we have found that the brain, the same areas of the brain activate for physical pain as they do for social pain. So, which makes sense to the fact that our bodies respond and our processes respond much the same way for both types of threats, right? The insula, I always do like to talk a little bit about. It connects body states to higher thinking. So the insula and the ACC are pretty near each other, and they work together a lot to integrate kind of these social mechanisms, our focus, our attention with where our body is, how the stomach's feeling, how the heart's feeling, what's going on in that, integrating that information to come up with then, what hormones need to be released, what do we need to do, what's going on in the body. There are spindle cells, which I think I talk about this later too, but there are spindle cells that they think connect between the ACC and the insula. And these spindle cells are believed to be very associated with self-awareness. And what's interesting about them is humans have the most amount of spindle cells. But there are other mammals that have them, I believe, like dolphins and elephants and so forth, but not as many. So this is part of the understanding of self-awareness. But when we link what we know about where our body is with what we know that we're attending to, what our attention is focused on, and what's going on in the world around us, this is a lot about our self-awareness. Okay, so that's our parts of the brain. So then how do we learn and we develop through this learning? Learning occurs, so stick with me here. Learning occurs as energy and information flows through the body and brain via neural networks as synapses are formed, connect, and communicate. So, when I say energy and information flow, I don't mean energy like woo-woo energy, which, can be that too, but I mean actually electrochemical energy flows through the brain, through these neurons, through, all these things, and what they carry through these neurotransmitters and so forth. So this information flow, carries the symbolic meaning that we have, and that information can be anything from, just sensory information of what we see, or it can be something as much as abstract thought. So there's information flowing through these electrochemical processes, like codes of a sort, as they all come together to create these things. So this energy and information flows to the body and the brain via these neurons and these synapses, forming synapses, actually forming the connections to other neurons, and they're connecting and communicating with each other. So webs of connecting neurons firing in a pattern allows learning to occur. And the more that they fire and wire together, the stronger the learning. Abnormalities in interconnectivity may underline some disorders like autism. So that's going to be another theory. There's lots of theories about autism: genetic, neuronal, hormonal, gut, flora. There's lots of different things about autism. Anyway, this is one potential. The neural net profile is the totality of various neural networks firing in a pattern together in response to an experience. So you can just think about that. It's all those webs, those spider webs that work together the moment something is experienced. Everything that kind of goes off at one time, that fires and wires at the same time, creates a neural net profile. Experience, in these terms, is identified as the activation of specific neural pathways. So when something happens, the stimulus of it comes into the brain, neurons fire and wire together. And so specific neural pathways, that's how we sort of transcribe experience. And it can shape our gene expression, can influence what genes are turned on and off epigenetically. Relationships are a primary source of experience that shapes how genes express themselves within the brain. Experience expectant development. So we have two types of learning, especially in these very early years that we're going to talk about. Experience expectant development. This is online like immediately. So neurons fire and wire together based on genetic instructions. So experience expectant learning is very much based on what the genes tell the parts of the brain to do. So genes instruct specific circuits to be created, such as the visual, auditory, emotional centers. So the architecture of the brain is set up within its hemispheres, within its regions, the occipital lobe, the temporal, all the different lobes and the two hemispheres that we have is run by that genetic coding, and it's all kind of in there. It's the blueprints for how to build the brain and all the different pieces and parts of us. So that's experience expectant. And so it creates, say, a visual center. And that visual center, through its creation, therefore expects learning, expects information to come in. And that's why we get experience expectant. It's expecting information. All of these centers are. Experience dependent development, specific experiences, I think I spelled that wrong. Experience dependent development is the specific experience within the child's environment that activates certain pathways. So these areas within the brain are set up. They expect experience, but what experience they receive is dependent upon the culture, the family, the place, the caregivers, everything that's out there in the world, and what comes in. What are the stimuli that they actually receive through experience to determine which neurons are going to fire and wire together, what the synapses are going to look like. And they strengthen existing synaptic connections and they create new ones. Or if they don't use those, the brain is a use it or lose it. This experience dependent is a use it or lose it. Unused neurons or connections are pruned away over time. If we don't use it, we lose it. So, we think about that in terms of trauma for children, for babies that don't have any experience. Their development can fall very, very far behind, and certain parts of the brain cannot grow accordingly. All right, so we have this brain, and it's set up to learn stuff, and it is reliant upon the environment to bring in information to it, to give it stimulus in order to fire and wire together. Now, and as it does, then it also has its own perceptions and thoughts and the things that happen to it as well that continue that learning. But it's all taking place within these connections between neurons. So a specific pattern of neural firing contains information within it, from simple sounds to complex thoughts. The firing of a single neuron or extensive neural networks, I'm not going to get big into this, some single neurons can carry some information, others require more networks that contain information, increases the chance of similar patterns firing in the future. So once something happens and it fires once, and it's an entire maybe network of neurons firing, it basically increases the chance that similar pattern will fire in the future. So now we have almost like, you can imagine this like neural, like very light trace of pattern firing, but we've traced it like an outline of it. And so there's a greater chance of that same outline firing in the future now. If the pattern is firing repeatedly, the probability of future firing is continually increased. So the stronger the wiring, boom, 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 it's getting more and more wired in there, the increased probability is how the network remembers. So we have created a probability when a neural network is first created. Now we also have a probability of that in the future. And that's what remembering really is a increased potentiality or probability of similar wiring in the future. So Hebb, who created the whole wire together, fire together, also said, basically, this is how he said it, we've shortened it, any two cells or systems of cells that are repeatedly active at the same time will tend to become associated, so that activity in one facilitates activity in the other, or neurons that fire together wire together and create neural net profiles. So once it's fired, and it's fired in linkage with all these others, now we have a greater probability that could happen in the future. I know I repeat all this, but I really I'm trying to get it in there, over and over and over again. All right. Information processing is a kind of more mod cognitive theory that compares a human knowing to a computer. Cognitive theory is always looking at how do we know things. Information processing looks at it as though the brain was a computer. So IP, information processing, looks at the way the brain inputs, processes, stores, retrieves, and outputs information, right? Things that computers do. So this is just the language we use. Memory is a major function of information processing and of learning. At birth, an infant's brain has an overabundance of neurons, but not as many synapses, because remember, it's just experience expectant. It hasn't, it's had enough experience in terms of some of its sensory information in the womb to create some knowledge and some knowing of sounds and tastes. Some of its all of its sensory places are online. But it has all of these potentialities that are waiting for that experience-dependent learning. So the synapses aren't as great, but the neurons are overabundant. Over the first few years, the brain becomes intricately interwoven with highly differentiated regions. So what that also means is that within the brain, we'll find as we move on that emotions are not differentiated so much in babies, right? Cry, laugh, all these different things going on, because the centers have not become differentiated. They do that with more and more experience. Genes, experience, and epigenetic tags will determine the patterns of the connections that we receive. So the genes will have something to do with it. What turns on and off based upon experience, what genes are turned on and off based upon experience in the outer world will determine what neurons fire and wire together. The exact structure of every brain is unique, dependent upon the experience-established connections and neural net profiles. Okay, so let's move. I am going to pause this one, and I'm going to start right back up on a second one, though. I'm talking about memory.